Net ionic equations. This is combining writing chemical equations from words into symbols, and then also predicting if the products will be soluble or insoluble. And so we have to look at a couple different things. First, you need to remember that when an ionic compound dissolves in water, the polar water molecules will break apart that crystal lattice and then surround the positive charges and then the negative charges. This results in hydrated ions. That means the water is surrounding the ions, evenly distributed throughout the water. So we are going to learn about a bunch of different equations, but they're all incredibly related. So a molecular equation is an equation in which the formulas of the compounds are written as though all substances exist as molecules. So this is what we've been writing forever and always. You know them. So please do note that it does include the states of each compound. So that means NaCl is in the aqueous state. AgNO3 is in the aqueous state. You will need to put these markings on your assignment tonight. They are necessary. An ionic equation then is an equation in which the dissolved ionic compounds are shown as free ions. Basically what has happened, so we're dealing with the same equation this whole way through, okay? What has happened is each of these compounds have broken apart where the ions exist. You can only dissociate a compound if it is in the aqueous state. So you will notice that AgCl has stayed as AgCl solid in the ionic equation. Also noticed in the ionic equations, you indicate the charges. And if we would have had them balanced, so maybe there had to be a 3 out here, there should be a 3 here as well as a 3 here. Okay? You need to keep all of the numbers associated with each ion the same. But I'm going to erase these just because they're not a correct part of this equation. Then we have to remove the spectator ions. The spectator ions are the ions that do not take part in the actual chemical reaction and is found in solution both before and after the reaction. What I mean by found in solution means that it has this AQ by it. So when you are looking for spectator ions, you only look at the ions that have the AQ. Then you look for, all right, is there an Na plus on the reactant side? Yes. Is there one on the product side? Yes. So that means they're basically canceling each other out. So we can get rid of them. Then you look at, all right, a Cl minus ion on the reactant side. Is there a Cl minus ion on the product side? No. That means it must stay. You cannot get rid of it. Then you look, all right, an Ag plus ion. On the reactant side, is there one on the product side? There is not an Ag plus ion. Ag is in the compound, so we cannot remove it. Then you look for NO3 minus. There's one on the reactant side. Is there one on the product side? Yes, there is, so we can cancel out both of those. Then you write a net ionic equation. A net ionic equation is the chemical equation that shows only those element compounds and ions that are directly involved in the chemical reaction. So that would be any of the items that we didn't cross off in that spectator ion when we remove the spectator ions. So we need chlorine, we need silver in order to produce AgCl solids. Cora?
Does it matter which element comes first in the reactant side?
No, it doesn't matter. They can flip-flop. What is that math property? Is it commutative, or where it doesn't matter? Like you could say 2 times 3 or 3 times 2. It means the same thing. It doesn't matter. Cl minus plus Ag plus is the same thing as Ag plus Cl minus. However, when you write your net ionic compound, the more preferred way to do it is to write the positive ion followed by the negative ion. So that's why they switched it around here. And so up in this first one right here, Na and Cl had been bonded together. So Na was written first and the negative was written second. But then when we took things out, it kind of looked, the negative was first, so that's why it got flipped around in that net ionic equation. Does that make sense? So the end result of this whole process is to get a net ionic equation. The goal of the net ionic equation is to show me how the solid is produced. Okay? A solid formed from a solution is called a precipitate. So up in this very first molecular equation, so basically what a precipitate is, when you have two solutions, so the AQ and the AQ, two liquid solutions, and they make a solid. So when I teach it to ninth graders, I've always said a liquid plus a liquid and you get a solid. That solid is called a precipitate. And it's a solid because this new compound is insoluble in water.
So there will be no liquids at all?
There will be no liquids. There shouldn't be. There might be a gas, though, like a hydrogen gas could be released. Okay? So, shall we practice? The first step is they're all going to be in words for you. And you need to write the equation. And the only way you will get the right answer is if you write the proper equation from the very get-go. This is where you need to make sure you know what's going on. So when you see copper 2 chloride, you must be able to write that as the proper compound in symbols. So copper 2, what does that tell you about copper? Copper has a +2. What is chlorine's charge? -1. So that means for copper 2 chloride, you have to have a CuCl2. And then it tells you it's aqueous. So you need to write AQ. And it's in solution with a potassium phosphate. What is potassium's charge? +1. Phosphate. Phosphate, not phosphide. Yep, phosphate is a -3. So that means to balance that, we need 3 potassiums to the 1 phosphate. Are you remembering this fun stuff?
I remember how much fun it was.
All right. They are mixed and they form a precipitate of copper 2 phosphate. So copper 2 we said was +2, phosphate we said was -3. So that means it needs to be Cu3PO4 2. And it tells you it's a precipitate, so what state do you put behind it? Solid, or S. And then what is our other product? It doesn't tell you, but you should be able to figure it out. Chlorine hasn't been used yet, and what's the other? Potassium. So that means we have some KCl. Is KCl balanced, charge-wise? Yes. Potassium's +1, chlorine's -1. And that will be aqueous. All right, so this is your molecular formula. I'm going to do, then we need to go and put our ionic, is that what it was called? Yep, our ionic equation. So that means, oh no, first we have to balance. That's our next step. You have to balance that molecular formula. So, fun. Let's see. We have 3 coppers on the product side, so we probably need 3 coppers over here. That makes how many chlorines? 6, so that means 6 over here. Potassium then is 6, so we got to put a 2 here, and that makes our phosphates work out nicely. All right, so you write the molecular formula, then you have to balance the molecular formula. Then step 2 is write the ionic formula, or ionic equation. So you start with 3 copper, and copper was +2, and it's in the aqueous state. This is a lot of things you got to remember for just one ion. Now, what would I write for chlorine? I'm just going down the line here.
Yes, you're negative 1.
3 chlorine. Do we have to put this 3 or not?
You have to worry about the 3, yes.
So 3 chlorine.
It will not be 3, however.
Yeah, it's put 6.
It will be 6 because this 3 times this subscript 2, there's a total of 6 chlorine ions there. 6 Cl minus AQ. Plus, what do I do for the potassium?
6.
Yeah, I'd write 6K charge plus, and it's in the aqueous state. Plus, how many phosphates? 2 phosphates, 2 PO4, charge is -3, and it's aqueous. All right, so then, since this is solid, the copper phosphate, the copper 2 phosphate, you just write that as is. No charges, you just leave that as is. Then we need to ionize or dissociate this potassium chloride. That'll give us 6 potassiums with a positive charge, and then also 6 chlorine minuses with the negative charge. So your product side should go much faster than your reactant side when you're writing these out. So now, once you have this step, you can go through and cross out your spectator ions. So if it's same on the reactant side and the product side, cross them out. And they have to be exactly same. So what are we crossing out here? Zoe?
6 Cl.
The 6 Cl minuses can go away. And then what else? Marta?
There's 6 potassium.
The 6 potassiums. So then that leaves us with our net equation. Your net equation is you just write whatever is left, as is. Although I do like what Cora brought up is try to write the positive ion first. So here we have 3 copper 2 plus aqueous plus the 2 phosphate 3 minuses aqueous, and it produces the copper 2 phosphate precipitate. All right, so we're only going to do one more of these example problems. The class picked to do the next one, but with this one, this hydrochloric acid, when you break that apart, you're going to get a hydrogen ion and a Cl ion. Hydrogen is going to be one of those that's going to be a gas. So just watch for that, okay? All right. Write the net ionic equation for the reaction of solid magnesium metal with aqueous silver nitrate to form aqueous magnesium nitrate and silver metal. So if it's telling you it's a metal, it's going to be a solid. Okay? So, well, let's start. We have a solid magnesium metal, So Mg, solid. Is magnesium a diatomic? Nope, so we don't need to worry about that. We're adding that with silver nitrate, AgNO3. Nitrate is 3, nitrite is 2, I believe. Yes, your polyatomic sheets will become your best friends again. However, you should start weaning yourself off of them if you can, because you're not going to get to use that on the CLEP test. Okay? So silver is +1, nitrate's -1. Okay, and that's aqueous. And then we make magnesium nitrate. What do I need to do here? NO3 needs a subscript 2 because magnesium is a +2. And that is an aqueous solution. And then we make a silver metal. Is silver a diatomic? Nope. Very good. All right, let's balance her up. Guide me. Cora?
Silver nitrate, NO2 from the silver and the carbon.
Very good. I believe that is it. All right. Step 2 is to write this as an ionic equation. So Mg solid. If it's a solid, it's not an ion. It didn't dissociate into anything, so you don't need to worry about the charges. Okay? However, our next one is in solution, so we do need to worry about the charge. Now, when we get to magnesium nitrate, do we need to worry about the charge on magnesium?
Yeah.
On this case, you do because it's in a solution. So MgAQ, and it's a 2 plus NO3, and there's 2 of them. If there is a 2 for that subscript, bring it up so it's a coefficient so it matches the reactant side. +1 AQ, and then +2 AG. That's a solid. Do I need to worry about the charge on that silver on the product side? No, why not? Because it is a solid. All right, our next step is to go through and cancel out the spectator ions. Where are my spectator ions? Zoe.
The 2 NO3s.
The 2 NO3s. Why not my silvers?
Because they're not the same. One's
They're
aqueous and one's
very good. One is aqueous and one is solid. So then for our final step, you go ahead and write what is ever left. Mg solid plus 2Ag plus 1 aqueous gets us Mg plus 2 aqueous plus 2 Ag solids. So then the last thing is predicting whether a product will be a precipitate. Is it soluble or insoluble? If it is a precipitate, the compound is insoluble. If something is soluble, it will be in the aqueous state. If it is insoluble, it will be in the solid state. This table will be provided to you for tests and quizzes. Okay, again, it is something you will become fairly familiar with, and it will just be there as a crutch, is what I'm hoping. But it is something that you will become familiar with. So, soluble things, if you look Under the ionic compounds, this first box, compounds containing alkali metal ions, lithium, sodium, potassium, rubidium, and cesium, or the ammonium ion will be soluble. So it doesn't matter what the anion is with them, the negative ion. If it has one of those 6 ions, the compound is soluble. Does that make sense, how to read this chart? So then the next one down, compounds containing the nitrate ion, the acetate ion, the chlorate ion, or the bicarbonate ion are also soluble. It doesn't matter what's out front for the positive ions. If it's got those 4 negative ions in it, it will be soluble. Mostly soluble are compounds containing the chloride ion, the bromide ion, or the iodine ion. Exceptions, this is why it's mostly, because there's an exception. Exceptions are those compounds that also contain silver, mercury, or lead too. So if it's silver bromide, it will be insoluble because the silver is insoluble. Does that make sense? All right, mostly soluble again are compounds that contain the sulfate ion. However, this would be an exception if there's silver, calcium, strontium, barium, mercury, or lead or with that sulfate. And then your insolubles. Compounds that contain the carbonate ion, phosphate ion, chromate, sulfide, and silicate ions. Exceptions are those compounds that also contain an alkali metal or ammonium. So if any of these are combined with any of these, it makes them soluble. Compounds containing the hydroxide ion are mostly insoluble. However, the exceptions are hydroxide salts and the alkali metals and the barium ion. So like I said, you will be provided with this chart, so don't panic. You'll just have to, process of elimination, go through all of these rules to figure out if your product will produce a solid precipitate. Did you have a question, Marta? Nope. Okay.
So, wait, so it's like saying on like okay, so say like on the bottom one, if the hydroxide was bonded with the Ba2+, whatever, that means that it would be soluble then?
Correct.
Okay.
All right, so let's practice this. All you have to do is predict if a precipitate will form when solutions of cesium bromide, so cesium and bromine, it doesn't even really matter what the charges are, and lead nitrate are mixed. So your first step here are to look at the 2 possible products that could be formed. So remember, the positives and negatives just switch partners. So now the products could be cesium with nitrate and lead 2 with bromine. So what you need to do is go back to the table from the previous slide and figure out if either 2 of those compounds are soluble or insoluble. So let's go back and look. So we have cesium, I'm going to just write them over here, cesium nitrate and lead bromide. So according to rule number 1, cesium is soluble. And nitrate is also soluble. So what state will this compound be in?
Aqueous.
They will both be aqueous. So then if we look, all right, mostly soluble, bromine, that's good. But then it says exceptions are those compounds that contain silver, mercury, or lead. Well, we have lead. So that would make lead bromide soluble or insoluble? Insoluble. So this lead bromide would be a solid precipitate. So this would be a solid